Okay, reviewing a solution that we got to a problem, I believe in the preceding class. We have two masses hanging over a pulley, one slightly greater than the other, and that slightly greater mass is going to be, the system is going to be released from rest, and the system will then descend in the direction in which the greater mass descends. Light frictionless pulley, so the only forces are those on these two masses. Now, the positive direction we've chosen for the motion of a single mass is downward. And in that context, the change in potential energy of the first mass being the negative of the work done by gravity on the mass, well, the force exerted by gravity on this mass is 10.05 kilograms times 9.8 meter per second squared acceleration downward. Since downward is the positive direction, that's the force. That force is going to be positive relative to this direction. And so is the 0.8 meter downward displacement, giving us a net work done by gravity of 78.8 joules, so that the change in potential energy being equal and opposite to the work done by that conservative force is negative 78.8 joules. Similarly, we calculate the potential energy change of the second mass, which is our 10 kilogram mass. Again, the force exerted by gravity is 10 kilograms times 9.8 meters per second squared in the downward direction, which is the positive direction. So we have a positive force here, multiplied by a negative displacement, because if this mass descends 0.8 meters or 80 centimeters, this one's going to ascend the same distance. And since downward is positive, that ascent is in the negative direction. So we're going to multiply that force by the negative displacement to get the work done by gravity. And then we're going to take the negative of that to get the change in potential energy, and we find that it's plus 78.4 joules, giving you a total potential energy change of negative 0.4 joules. Setting that equal to the kinetic energy change if the system is released from rest, we find that the final kinetic energy has to be 0.4 joules, so that the final velocity, solving 1/2 mvf squared equals to the final kinetic energy, gives us the 0.2 meter per second. And we did this again in a lot of detail previously. Now here we've looked at the system as a whole. The system as a whole has a net kinetic energy change of 0.4 joules. Also, the system as a whole has a mass of 20.05 kilograms. We have a total of 20.05 kilograms, all moving with the same speed, that speed being Vf. And again, that's how we calculate final velocity is 0.2 meters per second. Okay, now looking at the individual kinetic energies, the change in the kinetic energy of the first mass is, and actually I've got the subscripts wrong, this would be mass 1, this would be mass 2, let me correct that. Okay, we find that the change in kinetic energy of the second object, starting from rest, everything starting from rest, is just the 1/2 mass times the final velocity squared. We work that out, that's 2 joules, 0.2 joules. And kinetic energy for the first, 1/2 mass of the first, 10.05 kilograms, but to significant figures, that's still, to a couple of significant figures, it's not going to be any different. It's going to be very close to 0.2 joules, so that the total kinetic energy is 0.4 joules, as we assumed. It's just a little confirmation that this worked out correctly. Now, we want to analyze the forces acting on each mass. So for the first mass, we draw a free body diagram, which consists of just a point representing the mass and the forces acting on it. Okay? The forces acting on it are gravitational force and what else? Okay, well, all you have acting on this is gravitational force down and the tension up. So we have gravitational force and tension. That's it. And those two add up to our net force. Okay, so I'm going to kind of put that net force in yellow here to indicate that it's not really part of this diagram. It's really part of this, I'm just indicating here's the net force. How do we get that? We take our gravitational force and we add it vector, our gravitational force vector, we add it to our tension vector, and we get a vector about this long. And that's our net force. And of course, we can calculate the net force if we know the acceleration of the system, and we'll get to that. Okay, so we get that net force, and basically here we're going to be able to calculate the acceleration of this system. So we've got to get the acceleration of each mass, which allows us to determine the net force, because the net force is the mass times the acceleration. And we know the gravitational force. The only thing we don't know is the tension force. And since we're going to be able to calculate this, and we know what this is, we're going to be able to figure out the tension. Okay, so here's another picture showing our tension up, our gravity down, and our net force being the result of those two vectors. For the other mass, it's a 10 kilogram mass. It's a lesser mass. Okay, so this is the first mass. This is the second mass. This is what happens to M2. Now, M2 is actually accelerated upward, isn't it? So that means that the net force has got to be upward. What's that tell us? Well, it means if we put our tension and our gravitational vectors together, they're going to have to give us a net upward force, meaning the gravitational vectors have to be shorter than the tension vector, meaning that the tension has to be bigger than the gravitational force. And that's pretty obvious, otherwise the thing wouldn't go up. If you don't have more force pulling up than you have pulling down, then it ain't going to go up, is it? Okay, so there's the picture for the second mass. And it's important to understand those pictures and every aspect of those pictures. Now, how do we calculate the acceleration? Okay, well, the acceleration of the system is equal to the net force divided by the mass of the system. The net force on the system is what? 9.8 meters per second squared times 10 kilograms. Okay, that's the force that's applied to mass M2, because that's your 10 kilogram mass, and that force is going to be positive because it's tending to accelerate the system in the positive direction, the counterclockwise direction. The other force, the 9.8 meter per second squared times 10.05 kilograms, is acting over here, and you can see that that's going to tend to accelerate the system in the clockwise direction, which is the negative direction for acceleration for this system as a whole. So looking at the system as a whole with the counterclockwise rotation being positive, here's our expression for the net force, and that comes out to negative 0.5 newtons. Very close to negative point. It's actually negative 0.49 newtons. So we're making some approximations. We're going to have a little round off error here, but it's going to work out. Okay. So our acceleration is net force over mass. That negative 0.5 newton force is accelerating all of this mass. It's the whole mass that's being accelerated. If you were pulling down on this, you would feel the effect of this mass, wouldn't you? You'd feel a lot different than if this mass wasn't there, for a lot of reasons. Okay, maybe not a real good analogy there, but you can probably get the point. Okay, so the acceleration of the system is then 5 newtons divided by 20.05 kilograms. That's negative, indicating again the acceleration is in the direction opposite our positive counterclockwise direction. And that's negative 0.025 meters per second squared.